Tonight on Nova, Julia Child learns a new recipe. Take half a ton of flaked beef. Combine equal parts flour and butterfat. Stir in a few drops of industrial flavoring. Add a food technologist, market specialists, a panel of tasters, and a secret ingredient. Bake under controlled conditions in a special oven. And voila! That's how to create a junk food.
Major funding for Nova is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
Hi, I'm Julia Child. I'm making some little puff pastry appetizers because we're having some people in for drinks tonight. And I've rolled this up with cheese and I'm rolling it out again, and then it's got to be rolled 2 more times with cheese. And this whole operation takes about 3 hours from start to finish. It's awfully good. But if you don't want to go through all this folderol, somebody's already done the cooking for you. There's pizza, there are cheese puffs, sausage and biscuits, hot pockets, whatever they are. If you've ever wondered how all of these things were made, Nova is going to take you behind the scenes tonight at a British food technology company. We're going to show you the science of snacks. I'll be back after the show.
Something is happening to the food we eat. It's being subjected to a new kind of scrutiny. At research centers like this one in England, panels of expert tasters are taking part in controlled scientific experiments to try to identify that most elusive of food qualities, consumer appeal. Applying scientific analysis to the seemingly irrational human palate is a food industry desperate to put its finger on what it is that makes one product succeed where so many others fail. Food manufacture has become the domain of high science. The composition of food can now be explained in microscopic detail, its molecular secrets revealed. A new breed of scientist, the food engineer, now looks beyond conventional raw materials, manipulating and refining ingredients from unlikely sources to achieve novel effects. Food companies spend staggering amounts on product development, applying science and technology to a market worth billions of dollars. Their research and marketing strategies are often top secret. Peter Sampson designs snack foods. His British company, PA Design Limited, specializes in new product development. To provide us with a glimpse of today's high-tech food business at work, he and a team of food industry experts have put together a demonstration of how a new food is developed. So where do they begin?
Well, what you don't do is just think of a new clever technical idea and then try and persuade people to buy it. New product development is actually a creative process. It's fundamentally a creative process. But most successful new products come about through a very methodical, even scientific process, and a process in which you are constantly referring to the consumer.
According to the food industry, sit-down meals are on the way out. Instead, people have eating episodes, refueling without ceremony, often on the run. So Peter Sampson's team is designing a new eat-in-the-hand convenience food, better known to us as a junk food.
Hi, Sam.
Joining Peter Sampson at his office today is Malcolm Lightbody, a food technologist. They have arranged for consumer research to look at their competition in the snack food market. The research has been done by psychologist Mick Alt using a technique called product mapping.
Okay, as you can see, we've got 4 groups of products here, and I'll go through them one by one. In this group,
Mick and his team have spent weeks probing the general public's deepest feelings about snack foods.
And the characteristics that describe those products are that they are stodgy, traditional, and filling. Okay. If we move over here, you see we've got the crisps together with the salt peanuts. And the interesting thing there is tasty and crispy are actually highly evaluated characteristics. And over here, the sandwich and the croissant, well, they are nutritious and easy to eat. And then finally, the ideal product, and that's really our opportunity, which goes over there, should keep some of the good characteristics of the others, but it should be healthy, it should have no chemical additives, and it should be natural.
The team decides that product mapping has revealed a consumer need for a cross between a potato chip and a sandwich, but it must be natural.
So, Mick, if we take the sandwich area, then we're looking for a product with a nutritious and succulent filling with a soft coating on the outside, do you think?
Be crispy, because we know crispy is an attribute.
So indeed, a crisp bite with a soft centre.
You imagine, for instance, if you actually went for an integrated sandwich. Now, I don't know precisely what this is made of. You're going to tell us that in a minute, Malcolm, but some form of an outer case, which is savoury, crispy, all the attributes which the researchers identified that we need.
Yeah.
The inside is, in fact, again, fresh, succulent, whatever. Yeah. But it's an integrated product.
Yeah.
So, I mean, you could envisage this being a bite-sized sandwich, or indeed, once you go that far, it could be round, it could be any shape we like, but it would be a bite-sized, integrated sandwich. It's ravioli.
Well, it's a nice shape. It's nice and a nice graphic shape. You can have a sort of pattern stamped in the top. You can have a sealed edges all the way around, which was what you were saying, isn't it?
Yes. In technical terms, obviously, the higher the moisture content, the bigger the problem in terms of storage.
Well, we're going to give you a big problem, because I'm sure that the research will indicate that the more moist it can be, the better the product will be from the user's point of view.
It doesn't have to drip, of course. But
no, as long as it doesn't run up your sleeve. Now, let's ask you, how moist can we actually get it?
Well, my guess is consumers perceive moistness in 2 ways. One by added moisture, and the other by moistness that fatty ingredients can give.
The moisture is also the feel in the mouth, as opposed to the liquid oozing out of the sandwich.
Yes.
It's that sort of moisture that it's the mouthfeel which is important.
The new natural snack should be an integrated product with a crisp bite and a moist mouthfeel. Peter Sampson.
What we must now attempt to do is to generate a range of new product concepts within those opportunities. But it's essential that right from the very earliest stages, this is done in very close collaboration with the food engineers to ensure that the eventual products are both industrially and commercially viable. So the next step would be for us to go up to Cambridge to hold a series of what we call concept generation sessions with our colleagues from PA Technology.
At their appropriately high-tech premises, PA Technology provides one of today's growth industries, consulting to business. They advise food industry clients on how to use technology to maximum commercial advantage. With Peter Sampson is package designer Susie Palfrey. To provide a starting point for today's discussion, Malcolm Lightbody and home economist Carol Bacon have assembled some existing products.
Now, does everyone know each other? Susie, do you know Carolyn, who looks after the microbiology section, and Andy, who's from our process engineering side?
Their market research has told them the sort of product consumers want and the price they want to pay. The technologists have determined that to make a commercially viable product at this price, it must be made by efficient mass production techniques.
Can we have a little bit of thinking around the filling that we're going to put inside our crispy coating?
You could have 2 or 3 different fillings.
I'm sure you might eat a sandwich every day, but you wouldn't eat a cheese sandwich every day. So I think we're forced into looking for a range of fillings, all of which meet this ideal specification.
So fillings which are particulate, which have got a mixture of textures in there, which have got colour in there, and which indeed have some succulence, some moisture. That would be our ideal. The coating itself, we have positive comments from consumers about bread as a convenient coating, but we also know that a coating should be crispy and tasty. How can we get the best of both those worlds?
Could we think about filling something like this, which is going to be much easier to handle, isn't it?
Yes.
So where the filling is contained.
It'd be nice to have a single outer casing that could go down the production line, and a filler that just put in different fillings on different days.
Or something like pita bread, which of course you can slit open and fill with any type of savoury filling.
Because they've chosen to use a high moisture filling, a bread-like casing will absorb the moisture and tend to become soggy. The fat content of a pastry prevents this moisture migration, but gives a greasy taste. A product that's a cross between a pastry and a bread is a croissant.
Well, certainly it had some positive comments from consumers in terms of being a natural, healthy product, but perhaps difficult to handle. So, in fact, we could be looking for an improvement on that handling performance.
And whether you can make them industrially.
Yes, the production rate is going to define whether we can hit our price target. Yes. And I think we need to gather more information on that subject, and obviously Chorley Wood RA would be one useful point to look for extra information there.
A croissant is made from a rolled dough that contains interleaved layers of fermented wheat flour and butter. When baked, this forms the light, bready texture that characterizes the croissant. At the Flour Milling and Baking Research Association, they've taken frozen sections of uncooked croissant dough and examined them under a microscope. At this magnification, the separate layers of butter and flour stand out. Producing this dough is a traditional baker's craft. A layer of fermented flour containing plenty of the wheat flour protein gluten is folded over a layer of butter and rolled out. It is the gluten that gives the dough its elasticity. This dough is repeatedly folded and rolled, each time doubling the number of layers, which become thinner and thinner. But each rolling stresses the gluten, which becomes tough. The dough must rest for 20 minutes to relax it. If it is rolled again too quickly without a resting period, the gluten-bound flour layers break down and destroy the layered structure of the product. The traditional croissant doesn't seem like a candidate for mass production. But this small factory in West London, the French Croissant Company, has the capacity to produce 1 million croissants a day. They have done this by making a major capital investment in some highly ingenious manufacturing equipment that comes not from France, home of the croissant, but from Japan. The Japanese have cracked the problem of keeping intact the multiple fat flour layers in the dough without the usual resting stage. The fat, butter for a high-quality croissant, is extruded on the inside of a continuous tube of dough. When the machine is running, this tube is compressed into a butter and flour sandwich. It is then reduced in thickness by not one, but a series of rotating rollers that gently massage the dough. This rolling is so gentle that the gluten is not stressed. A resting stage is not needed, and the dough can go directly on to be sheeted out in overlapping folds to build up the multiple layers. The whole process is so far completely automatic and can run continuously 24 hours a day, with only the minimum of human intervention, but only to a point. Then Japanese technology runs out, beaten it seems by a design flaw in the product. To bend the croissant into its familiar round shape, 8 pairs of human hands take over. The technological solution to making casings for the new snack product will be to dispense with a costly team of croissant benders and produce instead a croissant with a difference.
There, the straight croissant.
They look nice.
Yes, they are. The pastry is the right texture. Now we have the problem of getting the filling into the product. I guess we could inject it into the product, but that's going to play havoc with the particle size. Now, the alternative is indeed to...
Make a casing with a cut croissant.
Yes, that's a good idea. So you actually have a filled cornet with a savoury filling.
Yes, then you could have your particles.
Yeah, and it would be handheld. It would be an interesting presentation.
From this simple idea comes the concept for the product, a filled cone. A trial batch of casings is made up using a croissant-type dough and taken to the next meeting of the product development group.
Now, today we want to take the idea of the filled cone and consider fillings for that product. We've put together a number of different ingredients, different textures, different flavors, from meat to fish to vegetable to cheese.
I think we should actually get in and try some of this, don't you?
Yes.
Yes, come on.
Let's try.
Be brave.
Anyone want a spoon?
Well, it looks nice anyway. Oh, that's strange.
Maybe the prawn
That's
one.
nice, actually.
Prawn and chicken.
Not what I was expecting at all.
You sound surprised.
Yeah, I am surprised.
Yeah,
That's chicken in a creamy supreme
Yeah,
white
okay.
sauce with prawns.
right.
Some of the combinations
So
are
we've got
slightly
some
unusual.
chewy texture from the
Yes,
from the chicken.
and from the prawns a whole. The chicken's cut up and the prawns a whole.
Yeah. I think there's always a danger that we show the particulate material whole when we know that we're going to get some breakdown in mixing and depositing. We're not going to guarantee to be able to reproduce whole prawns
I
or
appreciate
shrimps.
that. But at this stage, that is a danger because all of this looks so edible and so nice, but then it looks familiar. The skill here, I think, is going to be in maintaining as much of that presentation as we can when it becomes a sludge that you extrude into that corn.
Yeah.
To save money on the cost of these fillings and to prevent the meat from breaking down into a sludge, it may be possible to replace conventional cuts of beef with cheaper processed cuts. At the Institute of Food Research, expert advice is sought from Paul Jolly.
Well, the first thing is that you're not going to get something for nothing. There's no magic formula for upgrading really terrible meat. So because you want a good quality meat filling, we're having to start with good quality processing raw materials. So we're going to be using some cuts from cow carcasses, but from the better end of the cow carcass.
Even relatively good cuts of stew beef tend to have a high content of fat, which many people now regard as unhealthful. Here they have developed new technology to control the ratio of fat to lean as the meat enters the production line. It's called the Glyphoscan. Above a conveyor belt, a video camera scans the meat as it passes through. The video image is fed to a computer, which digitizes it. As each chunk of meat passes by, the computer works out the surface area of all the white, fatty parts. If there is too much fat going in, it tells the operator to load some leaner cuts until the overall fat-to-lean ratio meets the low-fat specification. Each batch of meat can then go on to the reformulation plant, where the blocks are broken up and mixed together. Reformulation transforms relatively cheap, tough meat into a more palatable, uniform product. First, it is chopped into tiny pieces. The meat is then flaked with high-speed rotating knives while it's still frozen. They have found that this shears the tough meat fibers into tiny lengths, producing a more tender final product. The next step is to add a combination of salt and a substance called sodium tripolyphosphate. What is it?
It is a simple inorganic compound which will help extract proteins from the meat, and those proteins will act as a glue during cooking. It has a unique action in being able to get pieces of meat to stick together.
Once a good bind has developed in the mixer, the meat is extruded into a large sausage casing for cooking. When cooked, the reformed meat has a firm texture and can be diced. For some tastes, it's a little rubbery, but meat like this is often used for lunch meats and frozen meat pies. To make the trial filling for the cone, the reformed meat chunks are simply added to a thickened sauce. In a production process, these fillings will be heated to pasteurizing temperature prior to filling. This will avoid the need for chemical preservatives, but heat treatment does have a drawback in terms of flavor loss. The cheese sauce suffers the most.
I thought it was quite bland when I tasted it.
I think it is. I think I was more, when I first tasted it, I was more affected by the texture of the taste, the tactile quality of it, which I think is very nice.
Yeah.
But in fact, the actual flavour is a bit bland, isn't it?
Okay.
It's a very mild cheese, if it's cheese.
They could, of course, use a stronger cheese, a blue cheese perhaps, or even better, a highly concentrated blue cheese flavor. This small test tube contains the flavor of 44 pounds of Danish blue at a fraction of the cost. It comes from this flavor house in London and was created by a special kind of food technologist, a flavorist. To make a blue cheese flavor, the first step is to find out what it is in real cheese that makes it taste the way it does. A sample of blue cheese is distilled, and the essence of blue cheese is passed to the mass spectroscopist for analysis. He injects the distilled sample into a gas chromatograph mass spectrometer, which vaporizes it. The individual molecules that make up the sample are recorded in order of their boiling points. In the blue cheese, there are over 100 different components, which show up as peaks on the screen. Analyzed further, each peak has a unique profile, the chemical fingerprint of the molecule. A computer searches its database to find a matching profile to identify what the substance is. The full list of all the different substances that make up the sample is handed over to the flavorists, who go on to produce the industrial flavor based on this information.
We've got the analysis back on the blue cheese.
Oh, that's good.
I think the first thing to concentrate on is trying to get the fatty acid balance right. And if you look at the butanoic acid, the decanoic acid and hexanoic acid, that should give you a good place to start.
The blue cheese flavor is then constructed to resemble the real thing using laboratory preparations of some of the chemicals found in the analysis. At this point, scientific method gives way to a little artistic license, all part of the flavorist's skill. John Wright.
Normally, you wouldn't recognize any odor just simply by one particular component. It's a very complex mixture. And the flavorist's first job is to try and get the individual components blended together in the right proportions to allow you to say, oh, that's blue cheese flavor.
The flavor is carefully built up item by item. The flavorist tests the mix not by the taste, but the smell. The nose is a finer instrument than the tongue. Industrial flavor is often a mixture of substances that imitate nature. Is what they are making here all that different from the real thing?
Chemically, there is no difference between the actual structure of the components that are used. The distinction is purely a legal one because at the moment you have an interest, a consumer lobby, if you like, for natural products.
In legal terms, if the flavor components are synthetic, that is, produced by a chemical reaction, then the flavor must be called nature identical in Britain or artificial in the US. Flavor molecules can be derived from almost anything. Turpentine, alcohols, and petrochemicals are common items in a flavorist's bag of tricks. But if, instead of being the product of a chemical reaction, the components are all extracted by physical means, such as pressing or distilling, and come from food or other plant sources, then the flavor may be called natural, even if the source is rather exotic, like this Masoi bark oil from the Far East. The choice of which type of flavor to use is often a matter of cost. The artificial one is significantly cheaper than the natural one. In the test kitchen, the technologists now have a number of samples of industrial flavors to choose from to put the missing flavor elements back into the otherwise bland fillings for the outer cone. Minute quantities are added to the sauce ingredients in a series of trial formulations. At this stage, it's largely a matter of trial and error.
Hi, Carl. I've made some more fillings using a new range of flavours.
They look very good.
The chicken one I'm particularly impressed with. If you want to try that one first. And then here.
I'd like to.
Tell me what you think.
Nice creamy sauce. And the flavour level in there, is it the new roast chicken we've been trying?
Yes, it's this one.
That's good. That's good.
You like it?
I think the creamy notes and the roast flavour come together very well.
What about the size of the particles? Do you think that's all right?
No, I think that'll go through the depositing equipment without any problem.
Good. If you'd like to try that one next, the savoury beef mince.
And again, we were using the same flavour or a same flavour company or a
No,
different one?
this was a different one. And again, that's a roast beef flavour.
Yeah. That smells good. Maybe a bit disappointing there. I wonder whether the onion flavour notes are covering up the beef a little bit too much.
That was a roast beef flavour I used. I did wonder if that was right.
Yes, maybe we need to go back to the flavour company on that and get them to tweak it a little.
Once the flavor balance has been tweaked to the technologist's satisfaction, a small production batch of cones is baked and filled. They combine the sought-after crispiness with a moist, succulent filling. The end result looks wholesome and natural. But will the public buy it?
The concept would seem to meet all of the design and technical constraints that we've established during the programme. All we have to do now is to actually test it with the consumer. But you can never tell. Many a seemingly good concept fails at this point. So let's just hope that ours isn't one of them.
Consumer research begins at this house in a London suburb. Mick Alt and his market researchers have assembled a group of what they hope are likely consumers of the new product, the filled cone.
Right, ladies, I've got a new product here. They're all slightly different fillings, and I'd like you to help yourselves to one.
Thank you.
The decision to scale up production and invest in manufacturing equipment has not yet been made. It depends on the response of groups like this.
I wasn't sure until I picked it up, actually, what it was, but there's obviously fish in there. It's in a different shape to what you'd normally buy. But the filling looks very appetising. It looks like chicken with a white sauce.
And this has got a mincemeat filling, so I think I'd probably like it.
Well, let's see. Well?
It's quite nice. I think the pastry isn't exactly to my liking, really. It's a little bit soggy.
It's very messy as well. It is chicken, but the pastry is too messy for me. I prefer something firmer.
The children might eat it if it was in a pasty case, but I still don't think you'd be able to eat it freehand like this. No, I don't think it would be very clean, especially not for children in the hand. I mean, I don't think it would go down very well in fast food shops, quick service places. It goes all over the place, as you can see.
They were really racking their brains to say something nice about it, but it was quite clear from that consumer group that product wouldn't have a hope in hell of succeeding.
How could the food technologists have been so wrong?
Well, I think it's because of their viewpoint of the world. They look at the world through technology and not through the eyes of the consumer.
The consumer research and taste panels on the first prototypes.
The food technologists did know they were on risky ground with a high-moisture, all-natural product. That's the problem with natural ingredients. They can be a bit delicate.
On in the programme, many of the respondents do accept that it's a fairly natural product and it's free from additives, but it's not seen as being particularly healthy.
They have to agree, too, that the cone can be a little messy to eat.
It's still naughty but nice, I think. You know, it falls into that category, really.
Yes.
You've got problems, Sam.
Some fast thinking is needed.
Perhaps look at some sort of barrier there.
Yes,
The technologist's answer is, not surprisingly, to apply more technology.
Any processing techniques that are going to help us down that track?
If we could move away from a cone, we could think in terms of perhaps an extruded product, maybe even using a cooker extruder, which would tend to give us a crispy outer, more of a biscuit texture than a baked product.
That's an excellent idea. One thing we need to guard against is having perhaps a uniform outer from the cooker extruder. Perhaps we need to actually get a more rugged external surface on the cooker extruded material.
Well, I think you may be able to, in fact, do something to the product once it's come out of the extruder, but I think that's something we could obviously talk over with the manufacturers.
Cooker extrusion is a new food manufacturing technique, very much in its infancy. But when set up, it can produce vast quantities of finished product in a short space of time. Within a cooker extruder, 2 rotating screws propel food ingredients down a tube, mixing, heating, and compressing them as they go. It works a bit like an open-ended pressure cooker. When the mixture reaches the end of the barrel, it is forced through a narrow opening in a die head, 1 or more slots like this, to make a flat cracker. As the product emerges, water droplets in the previously pressurized mix turn instantly to steam, aerating the product to form a crisp, bubbly texture. What they want, of course, is a filled product. This can now be made in one process with a system called co-extrusion. Process engineer, Andy Reynolds.
Well, I've established that we can co-extrude the product as we'd hoped. Examples being something like this.
It may be just the solution they need, the savory tube. But can this technique produce a natural product?
Well, I think, we can co-extrude and make a wheat flour with a high fibre outer material.
Yeah.
The latest technology may have solved one problem, but it has created another. They must think again about the filling. A high-moisture filling will make an extruded wheat flour casing soggy. They decide to replace the water in the filling with a vegetable oil. To experiment with different fillings, a mock-up of the likely final product is needed. This is Carol's department in the test kitchen. Her solution is ingeniously based on a conventional wheat cracker, steamed and formed into a tube.
So we're running a number of formulation trials to look at the cheese filling and also use these mock-up extrusion tubes for just to get a feel for the size and shape of the product.
This is the sort of product you're looking for?
From the cooker extruder work, we're looking for that type of product.
Now that they've established what the product will look like, the package design team has something to go on.
Hello, folks.
The designers have come up with 2 ideas. Cracked wheat savories exploits the fact that they now have a high-fiber wheat flour casing. And as an alternative, something a little more racy, the Go Natural bar.
Okay then, I'll just tweak the type up a bit and you can see it later.
While the designers are tinkering with the image that the product will have in the minds of the consumers, the technologists are still concerned about its performance in the mouth, its texture. A simple test of texture is to pierce the food with the laboratory equivalent of a set of human teeth and measure the force required. At the Leatherhead Food Research Association, they have developed something better: electromyography. David Kilcast.
Electromyography is the only technique available which can measure the texture or the change in texture of a product in the mouth during chewing. Now in it what we're doing is to measure the electrical activity in the muscles that are involved during chewing. And the measurements that we are making take into account all the changes in the product that take place in the mouth, such as mixing the saliva, temperature changes, right until the point of swallowing.
For each sample of food consumed, the trace of activity of the chewing muscles is analyzed and plotted out to give the food's chew profile.
What we're doing is establishing the chew profiles of a range of commercially available foods, and that will give us an estimate of the quality, the textural quality of those foods, which we'll be able to compare our new products against.
You ready? I'm ready.
From these chew profiles and market research, they know that consumers prefer a product that has an initial resistance to bite, but which melts away fairly quickly without clogging the palate, leaving a pleasant aftertaste. The initial bite resistance will be provided by the crispy extruded casing, but the other requirements will have to be met by the filling. There are a number of texturizing ingredients to choose from. An expert in their use, Mike Mars.
For a short, creamy, smooth texture, one of your obvious choices would be a modified waxy type of starch. Normally, when boiled in water, a waxy starch will swell excessively. If we take this to be an individual starch granule, you can imagine this swelling and disintegrating. In order to improve the situation, the starch granules are cross-bonded. Cross-bonding means that the internal structure of the starch granule is glued together, preventing excessive swelling in water. This produces a relatively short textured, creamy, highly desirable mouthfeel.
But something else must be added to make the filling more solid.
You have a wide range of gelling agents to choose from. All of these are extracted from vegetable sources. For example, pectins come from citrus fruits, alginates, carrageenans. They are obtained from seaweeds. We have gum arabic, which is a tree exudate. Locust bean gum is obtained from the carob bean. The two gums that could provide the gel texture which you're looking for are carrageenan and locust bean gum. Combined with a modified starch, you could in fact end up with the right kind of rigidity, bite, and smooth eating texture that you're looking for. Donna, this is a gel from a seaweed. It doesn't taste of anything, no colour.
That's good, that's fine.
Tell me what the texture's like.
Will do.
A sample of this suggested combination of carrageenan, locust bean gum, and modified starch is tested for its eating qualities. It performs quite well in the test. The chew profile shows a good initial resistance to bite, but it doesn't melt away in the mouth. It's a bit crumbly, a little rubbery, in fact.
Doesn't taste very nice.
Does it have any chewiness?
On its own, it does in fact taste revolting, but it will serve its purpose of binding together the emulsion of vegetable oil for the savory tube filling. And to get over the rubberiness, it may be possible to whip the filling into a foam to give it a melt-away mousse-like texture. An electron microscope reveals the structure of a foam. Interlinked protein molecules surround tiny bubbles of air, but in the presence of oil, they will break down. To make a stable oil-based foam, they will need something very new. Leatherhead Food calls it basic protein. It's still in early commercial development and is considered top secret. But it's claimed to be a modification of food-grade materials such as the normally acidic protein that comes from milk. Added in small amounts to a conventional whipping ingredient, such as egg white, it permits a previously impossible combination. As anyone who has ever tried to make a meringue knows, even a small amount of oil in a whipped egg white will normally cause the foam to collapse. With the secret ingredient added to egg white, the combination of proteins is strong enough not to be interrupted by oil. A foam can be made with up to 30% vegetable oil. Without basic protein, the oil breaks down the foam. The result is a runny mess. If this stabilized, texturized, foamed vegetable oil is used, it can be blended with natural ingredients and flavored with artificial flavors to produce a range of final tastes. Cheese flavor, fish, chicken, barbecued beef, anything they like. But will it be what the public is waiting for?
This is sample 789.
To avoid another flop like the savory cone, a more technological approach is to be used to test it. A computerized sensory evaluation panel. Their opinion is that the savory tube is a good-tasting combination of textures and flavors. But does it measure up as a natural product? Commercial success might depend on what they can say on their new product's label.
Hi Sam, Malcolm Lightbody. We've got the latest development samples here now. It's looking really good. We've got an interesting textured outer, and we're in fact going for the aerated cheese filling. And we've got quite a good mousse-like texture to that filling now.
What unique selling points can we legitimately actually put on the packaging though? Can we claim it to be a totally natural product?
No, I think we should at the moment steer away from a total declaration of all natural materials.
What can we actually say on there? What can I actually flash up there?
As far as the ingredients are concerned, we are not using synthetic colours or preservatives. We're using natural and nature-identical flavours. My feeling is that we can use a flash that says no artificial colourings or preservatives.
No artificial colourings or preservatives. Okay, well that gives us something to work on.
However, at PA Design, they have had some serious second thoughts about the name for the product.
Still concerned about the name. Go Natural. Sounds too much like a laxative. Really does.
Well, it is. Several people have said that, yeah. But I mean, if people are going to go natural, yeah. Okay, well then let's work something else on. If I'll leave it to you two, there's nothing sacred about go. Let's try and work up something else in the same general idiom, shall we?
Yeah.
Okay, well I'll leave that to you then.
Okay, Gary. My feeling is that we could actually resurrect the cracked wheat idea we had previously. I don't know what you feel about that.
It'd be nice if we could introduce something like that now. So Mrs. Beaton's cracked wheat.
What about my mum's name, Mrs. Palfrey? I mean, that's an old English name, isn't it?
That's quite a good one, eh?
Yeah.
Mrs. Palfrey's cracked wheat.
In fact, they come up with three quite different images for the same basic product. At the high end is mousse en croûte.
The mousse en croûte is clearly a sophisticated, upmarket positioning. It's overtly exploiting the French cuisine. It's a pastiche of French cuisine, I suppose. Mrs. Palfrey's cracked wheat savoury is a slightly less sophisticated positioning, slightly less pretentious. It's more friendly, and it has this implied heritage of Mrs. Palfrey, as though she were a person who actually lived.
Replacing the banished Go bar, the designers toyed initially with the name Crackos, before deciding instead on the much more catchy Crack-a-Snack.
Cracker Snack is the least pretentious, probably, of the three. And here the emphasis is very much more on the convenience side of the product rather than on cuisine or alleged cuisine. It's generally a more modern, more youthful presentation too. So that, I think, summarises the three different positionings that we're hoping to put into research. My personal position, I think, I would go for Cracker Snack, I think. I think of the three, that is probably the most credible in the eyes of the consumer, or will prove to be so. But then I've often proved to be wrong, so let's see.
Meanwhile, the cooker extrusion manufacturer, Baker Perkins, has been designing a machine to make the product. Andy Reynolds calls on designer Martin Fessler.
Morning, Martin. How's the die design coming along?
Oh, not too bad, thanks. We've got most of the bits made, you can see.
Oh, great.
Yeah.
The crucial part of the machine's design is the die head, which must combine the soft filling with the extruded outer casing.
The outer casing's coming from the extruder through these three openings there, and the cream is coming down that pipe, so we've got to have it wider there so that the cream can pass through. Okay? Product will then converge over there and pass through this outer die, so you get a ring of casing coming through there, producing a tube, and the cheese filling will come out there. Okay, Jeff, we brought you the new die.
Martin, this is the new size with the larger diameter insert.
Yeah, that should give you a 12mm tube.
The new die has been designed to extrude a casing through a 12mm ring.
That's right, yeah.
As it emerges, the product will swell, they hope, to about twice that size. Although small diameter products have run successfully, today's large diameter extrusion is breaking new ground. For this test run, a cream cheese filling will be used. The foamed mousse-type filling will be developed next, if today's run goes according to plan. It's the moment of truth. They're making the outer casing mainly from a wheat flour with added soy and milk proteins.
What are you doing now?
I have just filled the cream system up to the level of the pumps with cream, and have turned the oil priming pump on to fill the pipework from the cream system to the die head with oil.
The first thing to emerge from the center of the die is a stream of vegetable oil.
The idea behind the oil is to chill the die ever so slightly just before the cream comes through without burning on into the actual die opening.
Are we going to go, just before we start off, we're going to go back into cream?
Well, Jeff will be starting on the, on the plant now. We are on the cream now. We'll keep the cream running now.
We'll keep it going all the time while we get the extruder.
Yes.
The cream is a liquid as it first emerges, but will set to a solid as it cools within the casing. Within the barrel of the machine, the temperature and pressure are now rising. When the casing is fed through, it will cook in seconds. But should anything go wrong and the screws stop turning, the ingredients will instantly set rock hard and everything will have to be stripped down. When the filling is running properly, the pump is turned on, feeding the dry casing ingredients from a hopper into the cooker barrel. Soon they will see the co-extruded cracker snack emerging for the first time. The results are a little disconcerting.
That's a gruesome mess coming out there, isn't it?
The temperature within the cooker barrel is still too low to cook the casing properly. This will improve as it warms up, they hope.
Very quickly. You're aware of that? Yeah, it goes bloody hot.
As the casing begins to cook, the two ropes of extruded cracker snack are fed down a conveyor belt. At the other end is a guillotine that cuts the product into snack-sized lengths.
No, can we make these a bit longer? You know, they're too short.
Oh, yes, certainly, yeah.
More?
A bit more?
Yeah, that's fine.
Okay.
That's good.
The next problem concerns the diameter. They were hoping for at least a 20mm product from a 12mm opening in the die head.
Martin, the diameters are small. Do we need to change the die design to increase the diameter?
We'd have to put a larger diameter die in, and that'd give you a bigger product but keep the same texture.
Right.
But we'd have to shut the machine down and change the die parts to do that.
Right.
But if you want to just blow it up more, we can do that by changing the process.
Right. Can we do that now and just see what happens?
Yeah, okay.
To increase the size, the screw rotation speed is increased to raise the pressure in the barrel. The droplets of water in the casing turn more explosively to steam as they emerge from the die, puffing the product up with air. It is now a good 20mm in diameter, but they've forgotten something. A product this size hasn't been extruded on this line before.
The product itself is expanded too much to actually go underneath the safety barrier for the cutter itself.
The cooker can't be stopped or the screws will set solid. Meanwhile, uncut cracker snack is emerging at 80 feet a minute. Dropping the pressure a bit reduces the excessive expansion. But in the panic, the guillotine has come unplugged.
Okay, contact.
A roller added to the conveyor belt flattens the product slightly. A roller like this could also be used to indent the product to give it a more handmade appearance.
That's better, good.
At last, a slightly flattened but otherwise correctly dimensioned cracker snack comes off the production line. A sample of the finished product is collected.
This could be a successful product.
Cracker snack is a prototype product and may never be for sale. But the technology that makes it is with us today. Cracker snack is the food technologist's response to a consumer demand for a healthful and natural snack product. But is it really what the consumers had in mind? It certainly contains the natural goodness of wheat. It's the main ingredient of its outer casing. But whole grain bread never looked like this. Within the crispy crunch coating is a soft and bubbly mousse. A refined vegetable oil, held together by cross-bonded cornstarch, basic protein, locust bean gum, and seaweed. Its taste reminds you of succulent barbecued beef, of ocean fresh shrimp, of farmhouse cheddar cheese, of exotically spiced fried chicken. But its taste is largely due to a flavor which shares only a chemical formula with the real thing. A product like this is a triumph of food engineering. It is an ingenious copy of real food. And given the right product image, there's every likelihood that we will buy it.
Here we are, ready for the cocktail party. And I have here a really glorious selection of snacks from the lab. And with it, I would serve a very nicely chilled diet soda pop. And then over here, we have the French puff pastry cheese hors d'oeuvres, the feuilleté au fromage. And with that, I think a nice, well-rounded Sauvignon Blanc, which goes very well with cheese. So there you are, and a bon appetit. This is Julia Child.
For a transcript of this program, send $4 to Nova, Box 322, Boston, Massachusetts, 02134. Please be sure to include the show title. Major funding for Nova is provided by this station and other public television stations nationwide. Additional funding was provided by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And by the Johnson & Johnson family of companies, supplying healthcare products worldwide.